Let us continue our investigation of the magnetic force by looking at three more practical applications. So devices that depend on using the magnetic force. Okay, so the first one here is we need to understand a little bit better how charged particles move in a region with magnetic field. So what we have here is a charged particle with a charge Q moving in from the left, and it enters a region here with magnetic field going back into the board. So that's the green region. Now if we use the right-hand rule, assuming this is a positively charged particle, we would have our arm going to the right, the field goes down into the board. So check to see what direction the force would be. Yeah, so if we see that the force should be up here. So as it enters in, there'll be an upward force. The interesting thing here is that a force perpendicular to a velocity doesn't actually change the speed, it changes the direction. So what happens is that this particle, when it enters, begins to curve. We saw this when we looked at the demonstration with the electrons that were going across that tube being deflected by the field. Of course, then, if that velocity changes directions, the direction of the force also changes direction. So if we go a little farther, we find that this keeps happening all the way around. And the particle actually travels in a section of an arc, so a piece of a circle. If the particle had been negatively charged, it would have done an arc in the other direction. Of course, once it reaches the edge, it would then go in a straight line. It ends up that different speeds, if we think about it, should cause a different force and potentially a different curvature. So let's see if we can find the relationship between the speed the particle is moving and how much it curves. Okay, so what we know is that since the force is always perpendicular to the direction of the motion, there's no change in the speed. So along these paths, the speed is always the same. Okay, and so then it goes in a circular path, we know the acceleration. Remembering back from last semester. So that means the force should be like that. But we also know here that the field is perpendicular to the velocity, so the force is just the charge times the velocity times the field. So these two must be equal. So we find this nice result. So we could solve this for various things, but we could simplify a little bit first. We shouldn't be able to see that we could get rid of one of those velocities. So we get okay. Oops, that's not right. I meant to do this. Okay, multiplying by r and dividing by v. Okay, so if we solve for the radius, we see that if the velocity is bigger, we get a larger radius. for these curves. And if the magnetic field is bigger, we get a smaller radius. The same thing, we could look at the mass. If we had a bigger mass, we get a bigger radius. This is the basis for what's called a mass spectrometer. You send charged particles into this magnetic field, and then you measure the radius, and the radius is proportional to the mass. So that's a way of measuring the mass of a single molecule or atom. All right, the one thing in a mass spectrometer, you'd need to know what the velocity was. So you'd need to have a way of controlling the velocity. So let's see, there's another device to do that. So how would you generate particles all with a well-known velocity? And there's a very nice trick. So let's consider this situation here. So you have a source of charged particles over here just kind of flying out in all directions. And then you put a screen up so that you block almost all of them. So the only ones that get through are the ones going straight horizontal like this. Now they get into this region with a magnetic field, which here is going back into the screen, which would push those particles upward if they're positive and downward if they're negative. Okay, but we've also introduced an electric field perpendicular to both the velocity and the magnetic field. And if we think about the direction of the force on a positive particle, that force is downward, whereas the magnetic force is upward. So these are combating each other in a sense, and the stronger one will win. Now the important thing here is that the magnetic force depends on the velocity. So if the faster ones will have a stronger magnetic force, therefore the magnetic force will win, and these particles will bend up. So that's a fast particle. Whereas a slow particle, the magnetic force will be weaker and the electric force will be stronger. And it'll go down. And there'll be some speed where those two will be balanced and it'll just go straight through. So that will happen when these two forces are equal. The directions we're taking care of sort of by hand here. So we're ignoring the directions. They're not the directions, these are just the magnitudes. So we have QE, it's QVB, or if you will, V is U over V. So by choosing the electric field strength, which you could usually is done with parallel plates, so it's choosing a voltage, which is easy to adjust. Usually have a fixed magnetic field, but you could also change that. You set the ratio of electromagnetic field, electric and magnetic fields, and that chooses the velocity. So it's called a velocity selector. You can easily just dial in whatever speed you want, and you know that the velocity here has to be E over B. So the ones that come out of this box have a well-defined velocity. It's a very simple, elegant method of getting any velocity particle that you want. Of course, they have to exist in the first place over here, but you screened all velocities that don't have, all particles that don't have that velocity. That's why it's called a selector. Okay. So that leads us to one more interesting example, which is very similar, using the same effect, but you don't apply an electric field. So let's think again. Let's suppose about the same situation. We have a chunk of some kind of conductor here. Okay, so let's Suppose it's a chunk of copper. Okay, chunk of copper. And we have a magnetic field going in through one face and a current flowing through that chunk of copper. So it's really a piece of wire. So it must continue here, but we're just showing a little section of it. So on this section, there's a magnetic field going back into it, so passing through it. Okay, so we'll leave this 3D view now, but keep in mind that it is in 3D. So we're going to look at it again with the magnetic field going straight down in. So we're going to look at just this face here of the metal, and we'll redraw it. So we have a square piece of wire. We have a magnetic field. Going down into this wire, and a current flowing into it one end and back out the other end. All right, so if we think about this again, these are going to be pushed upward. This is the charged particles inside of it. The current's flowing all through the wire, so every place is getting pushed up. So what happens is that it's pulling the electrons away from this side and we're thinking of the conventional current. With building up charge at this side, so if there's positive particles flowing through here, it'll build up this positive charge up on that side, and it'll leave behind a negative charge on the other. Now, what happens then is if there's that built up charge, it will create an electric field like this. Of course, that electric field would dampen out these curves. It would cause them not to curve so much. And then less charge would start to accumulate, but it would still keep accumulating until this electric field built up to be strong enough that the magnetic force and the electric force are the same. And then all these currents would just go straight through as if there wasn't either an electric or magnetic field. Now, there's two things that you can get from this. But the important thing is that we built up a charge distance from one end to the other with an electric field. Therefore, if we take the electric potential difference between these two surfaces, now remember, this is actually the top and bottom of this solid chunk, right? So you can measure the voltage difference between that side and the bottom side. Let's say that this length here is D, and the length this way is W. All right, so this is the length D. So we know that potential difference from one side to the other delta x is from initial to final. So you see that delta x and e are in opposite directions, so it kills off that minus sign, and we just get e times the distance. what we know is that electric field is just the velocity times the magnetic field. So we could write it like this. So what we find is that the potential difference from one side to the other, which is something you can measure with a voltmeter, something you guys have all used, a very simple device, is equal to the velocity at which the particles are moving times the size of the wire in that direction times the magnetic field strength. So we could use this as a way of measuring this velocity. If we know the magnetic field strength and we know that distance, we just found the velocity, which is kind of nice. So you can measure the speed at which the particles are actually moving. We can take this one step further by remembering that we talked about this current before. So the total current is the rate at which charge is flowing through. And we decided that was equal to the charge per particle times the charge density, like the number density, how many charged particles are there per cubic meter, times the rate at which the volume of charge was flowing through. And that in turn was just the velocity at which the particles were traveling times the cross-sectional area of the wire, which we can write as that distance times the width. Okay, so the area of this side here is the cross-sectional area. It's just the distance on that side times the distance on the other side. Now we recognize here that we've got this V times D in both of these expressions. So rewriting this, we find that the voltage difference is the current we solve this for V times D, dividing both sides by the charge per particle, the particle density, and the width. Or we could turn this the other way. And we find that we can determine the magnetic field strength by knowing the charge carrier density, the width of the piece of metal, the charge per particle, and then the voltage and the current. So the voltage and the current are easy to measure. So again, this gives us a very simple way of measuring magnetic field strength. You're very likely to run into such a thing if you ever need to measure magnetic field. I think it's probably the most common way to measure magnetic fields. I think your phone likely has one. Okay, it's called a Hall probe. All it is just a chunk of wire with a known value for the charge carrier density, and then a careful measurement of the voltage and the current. Now, I had mentioned before, when we first talked about current, that for the most part, currents are carried actually by negative particles, electrons. But we think of it as positive particles going the opposite direction. And this situation here is the one place that we run into where it really makes a big difference. Because we come back to this situation and analyze it again. not assuming that it's positive particles moving to the right, but negative particles moving to the left. We get the opposite result. So I just want to remember here that we ended up with a positive charge on the top and negative charge on the bottom. So let's try this again. With the magnetic field still in the same direction. But now we're going to have the velocity coming this way, but with the charge being less than 0. So in this case, QV is still that way, so the force is still upward. Okay, so these particles will also deflect upward. Okay, so the charges will build up here, but now, just like they did before, but the charges flip sides. So now the electric field goes across in this direction. And that means the voltage difference from this side to that side is now negative. So this is actually how you can tell if your charge carriers are positive or negative. You set up a Hall probe like this, and if you get a positive voltage, they're positive particles. If you get a negative voltage, they're negative particles.